This problem with gears and shafts is from a past exam. You can pause the video, read it to see how it appeared in the exam. In this problem, there's a motor that drives a shaft, there's a couple of gears, and ultimately it connects to a saw blade. And the saw blade is pressed into a board. We know the direction of rotation and speed of the saw blade and the forces that the board exert back on the blade. And we want to know what are the forces between the gear teeth. We want to know the speeds of the shaft, the motor torque and power it delivers, and then draw free body diagrams of all the major parts. There's several phases of solution in this problem. The first couple involve surveying the system and deciding where we want forces and what the general motions are. We'll then review what you may have learned before about the relative motion of meshing gears and the directions of forces between meshing gears. And then we'll apply those ideas to determine the quantities that were requested in the exam problem. So we'll start by picturing the motion. The system here, the motor is stationary. We know the saw blade turns. That can only happen if the motor is turning the shaft 1, but it in turn must be connected to gear 1. It drives gear 1. So they rotate together. Gear 1 engages gear 2, but then for that rotation to be transmitted to the saw blade, gear 2 must be connected to shaft 2 and the saw blade. We know this is direction of the saw blade, like this. That must also be the direction of the gear 2. And so because of the engagement of the teeth, gear 2 goes as shown, so gear 1 must rotate this way. So what are the forces and the torques? Well, we now show the separate parts. Shaft 1 and gear 1 rotate together, so we can treat them as one part. And gear 2, shaft 2, and the saw blade rotate together, so they're a separate part. And we know the forces exerted by the board. What are the other forces or torques we could study? Well, we could study what's going on between the two gear teeth, and we could study what's going on between the motor and shaft 1. So we're going to review relative motion of meshing gears. We show a couple of gears right here. The two different gears will have different numbers of teeth. They'll have different diameters. But because the teeth have to be the same size, the ratio of the diameter to the number of teeth has to be the same. So, in other words, the amount of circumference devoted to each tooth is the same. So from this, we can get the speeds. We define the speed of gear 1 with omega 1 and omega 2 for gear 2. Because the gear teeth engage with each other, the two speeds are related. You can imagine if gear 1 rotated by one rotation and gear 2 had, say, twice as many teeth, then gear 2 would rotate just a half a rotation. So the speeds are the ratio of the teeth as shown here. And we can replace the ratio of the teeth with the ratio of the diameter, which is usually what's quoted for a gear. Now let's talk about the forces between meshing gears. You may or may not have studied this. So here we show two gears. We're going to zoom in on one part here. So now we see the meshing teeth. Gear teeth have a very particular shape. They have something called an involute profile. We sort of outline the shape of one tooth here. There's the shape of the tooth that is instantly pressing on it. Notice that those two surfaces meet at an angle like this. Since the gear teeth press on each other with normal forces, the friction between the gear teeth is usually pretty negligible. We know the force must be perpendicular to that line, so the forces have to be in this direction. So let's now separate the two gears. And we'll talk about the forces between them. This is the tangential line, and the gear tooth force has to be along that line perpendicular to the gear teeth. That force makes an angle, which we call the pressure angle, with respect to that tangential direction. But it's more convenient to think of the gear force is broken into a tangential and normal component. And we give symbols to those two components, the tangential force Ft and the normal force Fn. Furthermore, because those two forces are the components of a total force, which makes an angle of phi, the two components are related to each other by the tangent of phi. So we're now going to use what we learned to study the rotations of the parts. So here is the initial system. The blade rotates at 3,600 RPM, so we know that gear 2 rotates at the same speed. It is connected to the saw blade via the shaft 2. So now let's look at the two gears. We have the diameters of the two gears, and we found out before that the ratio of the diameters gives you how much one speed is different from the other. So if we substitute in, gear 2 is rotating at 3,600 RPM like the blade, and we know the ratio of the diameters, so we could determine the rotation speed omega. Now let's study the forces between the gears. So here we show the forces. These are the external forces of the board on the saw blade. We're looking to find the tangential and the normal force due to gear 1 on gear 2. Well, this is only a partial free body diagram. Notice we don't show any bearings. Bearings would exert forces that act through the center of the shaft. The one equation of equilibrium that is not affected is the moment about the axis of shaft 2. Furthermore, because of these shafts rotate at constant speed, we can say that all the parts are in equilibrium, so the total moment about the shaft axis is 0. And so two forces contribute to the moment, the 300 Newton tangential force and the unknown force Ft between the two gears. And so we can solve for that tangential force. And because we know the pressure angle for this gear, we could determine the normal force using the pressure angle of 20 degrees. We're now going to look at the motor torque and then the power. So here is the forces we just determined. This is a gear 2, shaft 2 in the saw blade and the forces on it. By Newton's third law, the opposite gear tooth forces act on gear 1. So we're going to focus here on gear 1. We're going to focus on gear 1. We show now there's the motor. We're going to remove the motor and we're going to draw the unknown torque exerted by the motor. This is one notation for drawing torques. That's not the one we want to use. Sometimes that notation in 3D is ambiguous as to its direction. Instead, we're going to use this. We're going to use this notation, the double arrow. The meaning of the double arrow is as follows. This little video shows you the thumb points in the direction of the arrow, and so that torque causes the body it acts on, shaft 1, to rotate in the direction of those fingers. So there's the directions of the fingers. So that's what that torque means. We're now going to determine that torque using equilibrium of the shaft. So again, we take moments about that shaft. The moment due to the motor, the torque due to the motor contributes, as well as the 225 Newton tangential force. We can calculate that motor torque. We can then compute the power. The power is the product of the torque and the speed, the angular speed. We have to convert the angular speed from RPM into radians per second because the standard unit of power in the Newton meter second system is watts, which is newtons per meter, Newton meter per second, and so we can't use RPM, we have to use radians per second, and so we can find the power. So finally, we're going to determine and draw the torques on each shaft and the gears. Here we show the torque again that the motor exerts on shaft 1. What happens at the other end of the shaft? Well, the other end of the shaft is connected to gear 1. So there we show the equal and opposite forces between shaft 1 and gear 1. What's the value of that torque? Well, if shaft 1 is in equilibrium, it's got to be 13.5 Newton meters. We show now just gear 2. It has the gear teeth forces on it, and it has the torque due to shaft 2. We show that as M2. Well, this must be in equilibrium, and so if we sum moments about gear 2, we can determine the torque M2 in shaft 2, and There it is right there. So now we show that torque with its magnitude acting on gear 2. There's by Newton's third law, the equal and opposite torque acting back on shaft 2 from gear 2. And we need to determine the torque between shaft 2 and the blade. Well, if shaft 2 is in equilibrium, that torque again must be 225 Newton meters.